Hello, everyone. This is Spencer Snolling from Hydromantis, and I'd like to thank you for joining us today for our regular monthly webinar. Today, we're going to be talking about modeling membrane aerated bioreactors using GPS-X. So this is a biofilm model, and we have two different unit processes for this in our table of unit process models. And so I'm going to be going through both of them today and talking about the structure of the model, and I'm going to talk a little bit about a case study that we did with one of them along the way. So my name is Spencer Snolling. I'm VP of Product Development here at Hydromantis, and I help put these two models together along with a number of other people at Hydromantis, and I'm glad that you can join us. This is basically the usual thing that we do with our webinars. I'll be talking today and giving some examples, running some desktop simulations. In the GoToWebinar dashboard, you will see a spot called the questions panel, and you can type any questions that you have there. And then when we get to the end of the webinar, I will hang around for a little bit and answer as many of those questions as I can. If there's any that are left over that we can't get to, I will follow up by email afterwards. So please feel free to shoot any questions in there. Okay, so the plan for today is basically I'll just talk a little bit about MABR technology as it exists out there in our industry. And then that will lead directly into talking about how we actually model that in GPS-X. So I'll be talking a little bit about model structure, what processes and what, things that, how we have to do the mass balance of all of the different parts of our wastewater stream in order to make the model work and be very predictive. That includes talking about the biofilm structure. It follows the same sort of biofilm structure that we have with many of our other biofilm models in GPS-X, like the IFAS and MBBR models. So if you've seen those webinars, some of this will be a little bit familiar, but it has a couple of important differences, though. So we'll go through those, and I'll talk a little bit about how we get the oxygen transfer. It comes from the inside in this case, as opposed to our other biofilm models. That'll lead to talking a little bit about the important inputs that you need to be able to use this model, how you specify the details of the setup and operation that you have, and I'll talk about how to plot and understand the outputs that you're going to look at in this model as well. And I will run a couple of desktop demonstrations as per usual to highlight the use of these two different unit processes. And then I'll talk about a case study that we have done that was a paper from 2-3 years ago. And as I mentioned, I'll answer any questions that we have at the end. Okay, so the membrane aerated bioreactor, MABR, technology is basically a situation where you have a membrane surface that sits in your bioreactor. And on that membrane surface, you are going to grow a biofilm, just the same as you would on any type of other media, except the idea is that surface is there to also not only provide structure for which the biofilm can grow, but also to be a permeable surface that will allow oxygen to come through and be transferred right into that very high concentration of biomass that's growing in your biofilm. So there are a few different vendors out there in the market that do this, and we have two different models in GPS-X that can be used to represent those. One of them is a hollow fiber membrane system. So that means that it's like a small tube. The biofilm goes on the outside and the air comes down on the inside. And then also we have a flat sheet system, which is sort of like two flat sheets together. The air comes down the middle and the biofilm grows on the outside where the liquid is on both sides and so on. So I'll go through a little bit of how those things look as we go. So these both more or less work exactly the same way. The key to modeling this is to get the correct amount of surface area for your membrane so that we can grow the right amount of biomass. And also we can do the right amount of oxygen transfer and diffusion of the substrates, the carbon substrates and ammonia and so on into that biofilm at the right rate. So this is going to be, like all biofilm models, a system that is diffusion limited. And so we want to make sure that we accurately represent that when we're trying to make a prediction in the future about how much treatment can happen with one of these units. Okay, so we've drawn a few diagrams here to kind of illustrate how this looks. So I'll start with the hollow fiber membrane. So if you can imagine, these are, and of course we've exaggerated the scale here quite a lot, but these are very small membranes that exist, and they hang down in that liquid. There's biofilm growing on them, and that performs, or that basically makes up an interface with the bulk liquid. The bulk liquid is your water that you are treating. It is the mixed liquor in your particular system. So that biofilm is there to, take up those nutrients, take up that COD. There can be biomass out in this liquid as well, and you'll see later that, of course, there's attachment and detachment to that biofilm system there as well. So you have this system of a fixed media, some biofilm that's growing there, and your bulk liquid. So in this particular case, the air is fed down into those tubes, and these tubes are actually not porous in the sense. They are very, very small, usually a few hundred microns or maybe a few thousand, where the material allows the oxygen gas to diffuse right through that plastic and right into that surface of that biofilm there. And so you'll see when we plot what the concentrations of oxygen look like in these layers, that you'll see a very high concentration right up against the surface there. So we have O2 diffusion in that direction, and then we have all of the other stuff that we want to be able to remove from the system being diffused in this direction. Excuse me. So the substrate is, in this case, the soluble BOD that we want to remove, and also the ammonia, and so on. So those are things that are diffusing into the system. This counter-diffusional activity allows for the biological activity to happen there and be very concentrated and optimized in this sense. Okay, so that was the hollow fiber version, and now the flat sheet version is nearly the same thing. It's basically looking at, instead of it being a tube, it's two sheets beside each other with a gap down the middle, and the airflow comes in, and we basically have the biofilm growing on either side with the bulk liquid surrounding the whole thing. And this system, and one of the arrangements I've seen, is sort of in a big wound spiral system as well. So there's lots and lots of surface area that way. So again, we feed that air, we have the diffusion through the membrane surface into the biofilm itself, and then we are bringing in and getting that diffusion of all the elements that we want to get rid of through there, and then that biological activity happens in that biofilm layer. Just for clarity's sake, the biological activity doesn't happen only in the biofilm. In our model, if you do have some biomass out there floating around in the liquid, it'd be much, much less than what you would have in the biofilm. But if you do have some out here, depending on whether you've got recycles happening or what have you, you will actually model all this the regular way that we normally model activated sludge. Okay, so to touch on some of the vendors that are in this industry, Suez has a technology, Zilong, which you can see here. They come in these large cassettes, but you can see the hollow fibers hanging down here. Those get dropped down into the tank, very much the same kind of concept. From Oxymem, same kind of idea there. I know that their materials are different, and they use them and they're designed to do different things, to perform at different levels. So, but the overall concept, the idea, you have a certain amount of surface area that you drop into an existing tank is how those ones work. And then the flat sheet one that I'm familiar with is from Fluence. And it is, as I mentioned, long wound spirals of surface area that allow the mixed liquor to come in between them and up and down. And these are sit in a larger vessel that can be then filled and lowered as well. So those are things that allow for a lot of flexibility in the designs of these things, and they can be very modular as well. So now both of these systems provide air inside the membrane, but it is possible, as I understand it, that you can supplement also in the rest of the tank with some air too. And we actually have that option available in the GPS-X units as well. So there's a lot of flexibility about the way these things are set up and the way that they are operated. So there's a lot of settings in the menus. They are, of course, some of the more complicated models that we have in GPS-X, but I think they cover a lot of the type of operation that you would typically see. And so we've had lots of luck and been able to calibrate our models to those types of systems, all three of those types of systems in the past. So what I want to do now is talk about how we actually model this. And I won't go into as much detail as I might normally when we've talked about biofilm models. I actually did a couple of times more detailed webinars on how our biofilm models work. So I will suggest if you want to get into the details, the nitty gritty of kind of what shape of equation are we using for attachment and detachment and all of that kind of thing, how all those parameters work. I would recommend watching one of the other older biofilm webinars that we have on our YouTube channel. It's the same equations that we're using here, but I will review the way that we do this. So what I want you to do is sort of focus on a slice of this particular reactor with the liquid and the biofilm and that membrane surface. So if we blow that up and we have the membrane on the left, so over here, this is a membrane through which we will be diffusing gases, oxygen primarily. We have 5 biofilm layers, and these are treated in our model like 5 individual reactors. And then we have one more reactor out here, which is the rest of the bulk liquid. Now I'm showing it as blue, kind of implying it's really clean. It actually is usually going to be wastewater, so it will be mixed liquor potentially. So it could be, if you have a recycle, it could have a potentially significant amount of biomass in it, or maybe it doesn't. There's a lot of flexibility. We model it the same way, whether you go one way or the other. Okay, so to cover off the types of things that we are doing, the processes that we are including in our mass balance of all of the COD and nitrogen and phosphorus and all the other components. We have, first of all, attachment and detachment of solids. So this is something that takes solids that are floating around in the bulk liquid and attaches them and detaches them from this first outermost biofilm layer. So this is something that has a rate constant that you can control. You can turn the attachment up and down, and it could be a function, say, of mixing or something like that. Depends on how you want. I have always found that our default values work. Under 90% of the situations, our default parameters work fine. Occasionally, I may find the situation where the biofilm thickness that we're predicting might be a little bit on the big side, and I might turn up the detachment just a little bit, just to knock it back. So generally, it's fine. We then, of course, have one of the most important aspects here, which is diffusion of the soluble components to and from the bulk liquid. So in this case, a lot of the time it's going to be in the direction going to the left here. Basically, we're taking the ammonia. There'll be a diffusion gradient that wants to go into the biofilm. This raw wastewater out here might have ammonia of 20 or 30 milligrams per liter. Hopefully it's a lot less in here if this biomass is doing its job. So the diffusion is going to want to move into, and it actually will continue to diffuse into the further layers. We do a mass balance across all of the layers here right through to the back one. And as well, we also have internal solids exchange. That's really an equation that allows for equilibration of the solids as they are moving around in here. So since we're predicting biomass growth in each of these layers, we're having biomass that is, born and growing and getting to the end of its life and dying and forming inert materials. And those inert materials will, accumulate and eventually will reach an equilibrium where some of those things are going to be pushed out to the outside and eventually detach and go back into the liquid. So just to be, clear about it, we do not model like sloughing events, but we do model a continuous detachment of solids. That's the steady state equivalent of a sloughing event. So basically what you're going to find is, of course, that we have a net gain of soluble materials in here. We have growth, and then we're going to push out some solids and they're going to detach. So, but in general, these 5 reactors are modeled with the biological models that we have in exactly the same way that we would do any of our other biofilm. And in fact, it is the same way we do the liquid stuff too, because basically we're using our Mantis 2 model or whatever model you have picked to model the biological equations in these reactors. There's not anything different about the biological part of the model. It's just we're operating at much higher concentrations, and then we have these diffusion terms and attachment and detachment things thrown in there on top. Okay, so that is what is going on sort of in all of this. Oh, sorry, and I forgot, the other important part too was, of course, the diffusion of gases across this membrane surface here. So now, primarily the main one that we're worrying about is, in this case, oxygen, but we do also take care of the other gases, mostly because we have to mass balance the gas across the entire thing altogether anyway. So, so we're going to specify, one of the key things is to specify this oxygen mass transfer coefficient. that is appropriate. And that is a parameter that you can calibrate and an important one to consider when calibrating your model. Okay, so what I've done here is I've divided that concept that I just explained actually into 4 parallel units. This is actually the way that we sort of view the model when we have things running in series. So, and it works this way actually for all of our biofilm units. We, by default, have several of these things running in series. And they represent, in a, say, for example, a trickling filter. This would be the flow coming in at the top of the trickling filter. And then this, there's like an effluent from this particular part of the bulk down to the next one and down to the next one. And each layer interacts with its little section of biofilm. And you get these little sections of biofilms that have different concentrations, and they kind of make up a really interesting profile. You may find, of course, your biofilm distribution is a little bit different at the end than it might be at the very beginning. And so in the MABR models, it's the same thing. These are units, these are reactors or modules, I guess you could say, reactors in series. And in the flat sheet, we basically just have one big one, like one in series that you can set to 2 or more if you like. In the hollow fiber, we actually have it set similar to our plug flow tank. So it is actually 4 tanks in series. So you're going from upstream to downstream with the liquid flow moving along. The biofilm remains fixed in its spot and is going to grow based on the loading that it sees. Okay, so now let's talk about the input parameters that you require when you drop one of these things on your drawing board. Just like in all of our other GPS-X models, there's quite a large number of input parameters, but a lot of them you don't have to touch. It's basically the most important ones are the ones I like to highlight in these webinars, are related to making sure you get the right size of everything. That's the most important key, right? What is the volume of a reactor? What surface area do you have for flux? That kind of thing. Get that in there first. So, and then there's often some other parameters that are sort of more calibration ones where you may want to adjust it and try to fine tune your performance. So for the hollow fiber MABR, one of the key things is to get the volume of the tanks for setup before we even start talking about the fibers themselves. So in this case, you can set the tanks in series. As I mentioned, it's 4. Our drawing actually represents 4 tanks in series with these hollow fibers hanging in there. And you set the volume. This is basically exactly the same as a plug flow tank menu. But when it comes to the specifying the details of what are the surface area that is available to grow biofilm on in here, there are these details that are specific to hollow fiber. So what is the diameter of the thing, and what is the length of the modules, and how many do you have in there, and so on. So these are basically there for us to multiply all these numbers together and come up with a surface area. That's what we really need to know in this case. There are a series of other biofilm related parameters, such as, the biofilm thickness, attached liquid film thickness, and so on. These are basically exactly the same as they are in our other units, although we have calibrated them specifically for MABRs. Now, in other words, this maximum biofilm thickness is a relatively important parameter. So you would find, for example, in our trickling filter, this would be a bit of a higher number than you would find, say, for example, in an MBBR unit. So given the experience we've had with the development of these MABR units, we've found values that are comfortable, and those are the defaults that you will find in those menus. Okay, so for the flat sheet, same thing, set up the number of tanks in series. So you can see here that these are reactors that water will flow through. This actually is supposed to be representing basically 8 of these things that are in parallel with each other. So there's really only one surface area that we are dealing with here. Now you can actually repeat that by making it 2 or 3 or 4 that would represent groups of this thing as you went along. But by default, we've got one set. Now you would set the number of spirals and the area per spiral, and that is the thing that takes up, gives us the information that we need to calculate the correct surface area. And then the biofilm parameters are once again exactly the same story as before. We need those to be able to calculate all the details about the biofilm, make sure we get those 5 reactors designed correctly, and then start applying that diffusion and whatnot. And again, we've got good default values for these things now. Okay, so that's physical parameters. That's just getting everything set up so that it accurately reflects the system that you have. Okay, so now for operational, which is the other main thing that you need to make sure you have done correctly. For the hollow fiber MABR, we have an operational menu, which is where you're going to define the aeration going on in your system. So you'll see here that for this particular unit, we have a model that is available with this pressure difference model that is available where you would specify not an airflow, but rather what is the pressure that you're applying the air at and what is it at the end and your oxygen fraction in air. This is all something that we, again, worked with and calibrated to. It's actually part of the case study that I'm going to be showing you at the end of the webinar today. So these values are all pretty realistic and pretty normal, so you could use those or you can adjust them up and down as appropriate. The only one that I would say you maybe want to adjust a little bit is this mass transfer coefficient. That will help you make sure that you get the right amount of oxygen coming into your system. It's fairly straightforward thing. You just turn it up or down, and turning up gives you more air, et cetera, et cetera. This aeration setup at the bottom of this menu, however, is referring to any other diffused air that you have in the bulk liquid. So this is basically the regular diffusion that you would get in a normal conventional plug flow tank. So you can do both of these or just the aeration above, and just the stuff that comes in through the membranes. So you'll see that we actually have that set up in the case study as well. So I'll note here, we actually turned off the diffused air by default. So it says entering airflow is our option as opposed to using a DO controller. And by the airflow is 0. So basically, the only air that will come into this system by default is what makes it into the biofilm through diffusion through the membrane. Now, generally, that means that you're not going to see any DO in the bulk liquid because it's coming inside, it goes straight into that biofilm, gets used up there pretty much. It's not, it's not a way to aerate all the liquid in the rest of the tank. It is really there to just aerate and provide oxygen to the biofilm. I will mention, by the way, this model, this kind of surprised me when we got into the development of this. This pressure difference model actually came from a paper that we were given by one of the people we were working with at the time. This is from 1989, actually, this paper. So it was interesting that this technology has had quite a long history in many stages of early development. So. Okay, so we have, for the flat sheet MABR, a somewhat more straightforward way to specify the oxygen transfer here. So again, it's an oxygen membrane diffusion mass transfer coefficient. So basically, it is a KLA value across that membrane. So you can specify the details about, how much oxygen you're trying to transfer at any given time. So this can be something you could control, and I've seen situations where this has actually been used in concert with one of our timer controllers so that it will allow for alternating aeration. Sometimes the air is on, sometimes it's off, and you can, by doing that, here set this, alternate it between 0 and some other value. That's actually a really sort of, sophisticated way in order to do some interesting process control here. So. A note again, we also have the ability to do regular diffused aeration from the bottom of those reactors there. And again, by default, we've got that set to 0, but it's something you could take advantage of to aerate the bulk liquid too. Okay, so that's a fair bit of input. And now I'm just going to talk a little bit about the output. Now, I think it sort of warrants a little bit of an extra explanation because I like to take advantage of the two-dimensional graphs that are available in this particular unit, and actually any of our biofilm units, because it is, once you understand in the orientation of what we're displaying for you, then it becomes a very useful and very intuitive way to sort of summarize a lot about what's going on in these particular systems, right? So you have the option to look at the concentration profiles through the biofilm layers for any one of those particular reactors. You can look at the profile of the concentrations in the liquid as it goes down, and you can even look at the biofilm thicknesses and other things that are going on there. So most of these can be found by right-clicking on the object itself and going to the display variable menus. You click in the middle of the object, you will get a menu that looks like this. And as you can see, it's pretty long. It's actually, I think, the second longest of all of the objects in GPS-X. I think the SBR is the one that has the most. But nonetheless, it is a lot of details and lots of information to manage, but there's lots of very rich information to be able to put on your graphs and take a look at. And we're going to do that here in this demonstration in a moment. So the ones that I think are the most useful are to look at the biofilm profile. So that's a one-dimensional, and we're going to show it as a bar graph, a one-dimensional vector of concentrations through the biofilm. And by what I mean is, like, as you penetrate into the biofilm. So it is basically the concentration in the liquid, then in the first layer, second layer, third layer, as you go deeper into that biofilm. And you can see, you know, that gradient of those soluble concentrations. Another one is to look at the concentrations in the reactors as you go through that particular unit. So, you know, we're going to take a look at that as well. And that is basically just looking at the same way you would look at a profile in a blood flow tank, except that we're just going to be looking at, in this case, only the liquid concentrations as we go. But the one that's the most useful is basically the 2D image. It's concentrations of the liquid and the biofilm together all in one surface. And I'll show you shortly how to sort of orient yourself on that one. I will note that there's a lot of other performance variables that we were using and calculating as part of some of the calibration efforts that we've done over the past several years. And sometimes we calculated up extra special things, you know, nitrification per surface area and all those kinds of things. We've collected up a number of those variables and put them in this menu for you as well. Okay, so just to sort of distinguish between those things, here's what a biofilm profile looks like. And so this is dissolved oxygen. And you can see here, on the left, always on the left, will be the bulk liquid itself. So this is the concentration of oxygen in the liquid. It's pretty much close to 0 in this case. And the right is the biofilm as it's up against the media surface. So this is right next to the surface where the oxygen is being delivered in an MABR model. If we were doing IFAS, these bars would be the other way around because the oxygen has to come through the bulk liquid. Here it comes through the media itself, and so that's why the higher concentration of oxygen, almost 2 milligrams per liter in this case, is on this side. Okay, this is a different graph. This is concentrations in the reactors, the second one that I mentioned. So this is only liquid concentrations, and it's for the 4 reactors in series. So basically this is upstream and this is downstream. So we go from left to right as we go through our units and then onwards downstream to the rest of the treatment plant. So kind of fits with the way that I would say most people draw their wastewater treatment plants on the drawing board in GPS-X. And these are the 2D concentration variables, which is essentially combining those two concepts together. So each one of these rows, as it goes from front to back, is the same as doing the biofilm profile. It's just that we're going to stack them one beside each other for those units as you go through them. And so basically, I'm just going to jump ahead to this one. Basically, the 2 axes you need to know are this one. This is basically reactors along this axis. So this is basically going from the upstream end to the downstream end as we go from left to right. So this is basically passing through the system before it goes on downstream. This is then the biofilm layers along this axis. And in the front is the bulk liquid, and in the back is the media. So keeping in mind here, this is oxygen. So that means in the front, it's completely anoxic out here in the bulk liquid. But in the back, up against the media where all that oxygen is coming through, basically we're seeing higher concentrations of oxygen at the back there. And it is the difference, the edge, the interface between this first and second layer. That's basically the liquid biofilm interface. The second row is the first row of the biofilm, and then 2, 3, 4, and then the 5th one at the back here. So as we go from left to right and we go downstream, you can see actually the oxygen was increasing here, which is maybe not too surprising. That would be the same as if you were to provide an equivalent amount of airflow to a plug flow tank. At the front end is where most of the the loading is going to be. So you're going to have a little bit less residual oxygen there. But as the substrate and ammonia gets used up, then you're going to have a little bit leftover oxygen, more so at the end of the system. We can see it's even bleeding through to the second layer here a little bit too. Okay, time for a desktop demonstration. Okay, so here's my copy of GPS-X, and I'm going to go to the sample layouts menu. in the sample layouts menu, you will find the unit process example. So I always try to suggest to people, if you're a little unsure about how to use one of the GPS-X objects that's in the table of objects over here on the left-hand side, come and look in the unit process examples and see if you can find that object in here, because usually these are, every time we make a new object, we put a new sample layout here that has lots of descriptions about how to use that and what it's all about. So I'm going to pick the the hollow fiber MABR unit first. And I'm going to run a steady state simulation, and we'll take a look at what's going on in this particular system. So you can see here, wastewater comes in, primary clarifier, then we got an MABR followed by a regular aerobic tank and a secondary clarifier, and then, you know, the usual solids handling. So let's just take a look at what's going on in this MABR unit. So first of all, we can take a look at the usual way that we would look at a summary of the results going on in a system. This particular system, as we can see here, has a recycle, so we would expect to see some mixed liquor here, 1,700 milligrams per liter. That's normal, of course. We can see our ammonia is dropping from 25 down to 7, so we're getting some nitrification happening there. Just across this unit, before we even get to the aeration, the regular aerobic plug flow. So let's see here. If I go to this biofilm profiles, this is the part that I wanted to take a look at what's going on here. So this is actually the same screenshot I was showing on the slide. So we can see here that we have, 0.8 all the way up to 1.6 milligrams per liter in that outer biofilm layer. So the inner biofilm layer. As I mentioned, the media is at the back here. So up against the media, we're getting lots of oxygen, because that's the way this is designed to deliver it right to those concentrations there. So we can see then, if we look at the ammonia comes in here, and of course it's going from left to right. And as that ammonia diffuses into the biofilm, it's being nitrified. So you can see at the lowest concentrations are at the back, up against where all that oxygen is. And we can see that we've got some nitrite and nitrate in here as well. I'm going to come back and talk about this a little bit more later on, but you'll notice that the heterotrophs kind of grow up front here. They're kind of, well, they're sort of everywhere altogether. But if you take a look at the AOBs and the NOBs, they're growing actually in the back. They're basically growing up against where the aeration is the most. So it's always an interesting situation then that you can provide oxygen here at the back, and then that's where all the AOBs and NOBs are. So you're going to do that nitrification, you know, up at the back side, and then out on the front in the interface with the liquid where it's anoxic. Up here, you can be doing denitrification. So, you know, there's a nice balance there of doing that. Okay, so that's what this particular unit looks like, and there's lots of other details you can dig into if you want to play around with that layout. So let's go back to unit process examples, and we will take a look at the flat sheet example here, which is a different kind of setup, but it's something similar. Anyway, you can see we're going to run a steady state solution of this as well. And I've set up a few profiles for this one as well. Similar concept again. We can see the ammonia going down. I actually put quite a lot of variation in this particular example. DO is at the back, and we can see here the nitrate is up at the back there, and this is going down. Now, as I mentioned, these units are sort of filled together in parallel, so that's why we're really treating them as one giant continuous biofilm surface. So we're only showing one here. But as I said, the model is totally set up to be able to create multiple units in series if that is what you're using, and that's what you like to do. We can combine them all into one GPS-X unit, or you can even drop two of these on the screen and do it that way. But I like to be able to fit them all into one graph on via this method here. And we'll talk about a case study. Okay, so I'd like to talk a little bit about a project that I was involved with when we were developing the hollow fiber model. And we were working with some engineers from GE at the time, which is Suez now. And we published this paper at the WEF specialty conference, the Nutrient Symposium that they did in, I believe it was Florida in St. Petersburg, maybe, in 2017. And so if you want to dig that paper up there, nutrient removal intensification with MABR, and it was supported by doing a process model. It worked well because they had been running a pilot for quite a long time, over a year, and they had a lot of really good data, so we were using that to calibrate the model with. So this was a pilot that ran for 500 days there from April 2015 to September 2016, and it was using, conventional municipal wastewater. They had 4 reactors in series, and for a total of 6.8 meters cubed, so it was quite small pilot scale. And they had the ability to have 2 zones up front that would be anoxic or at least unaerated, and they ran part of the time with some MABR reactors in there and some of them just on their own. But the part we were interested in was when they had the MABRs in there. And then they followed that by 2 aerated zones. So it's not unlike what I was showing you in that sample layout. They then had a secondary clarifier and a recycle. The clarifier was quite large, just so that it wouldn't be the rate limiting step in this process. So it kind of looked like this, basically. And so they were feeding it with primary effluent that was just regular flow from the plant, the main full-scale plant there. And the typical medium strength municipal wastewater here in Canada. Guelph is only about an hour away from where I am right now. And influent flow rate, 22 meters cubed per day. And the idea was they were going to operate it at, well, a number of different set points to do different investigations. But the part we were interested in, they were operating it there between 4 and 8 days of SRT with a recycle ratio of 1. And their mixed liquor was in, normal mixed liquor range of 1,500 to 2,000 milligrams per liter. And just for the sake of completeness, here you can see the influent characteristics, typical North American wastewater. Oh, by the way, I will mention, in case you do happen to notice, that the soluble phosphorus was pretty low is because actually it was primary effluent, so it was after they'd already precipitated out a fair bit of phosphorus, and it had been taken out with the primary sludge. Okay, so we selected from all of that data a period to be able to do model calibration with. And we wanted a period of time that was relatively stable. There were a number of what I guess you would call upsets in this pilot, and there were quite dynamically changing things happening at the plant while it was going. But we were able to get a good chunk of data in this time period right here, which we called the modeling period, where the performance of the system was actually relative. I mean, there's a few outliers here and there, but generally it was reasonably flat. And the average performance or the average loading to the plant was reasonably consistent during that time. So we wanted to be able, particularly for the BOD removal, and it was actually the nitrification, denitrification part of it that we were really most interested in seeing how well we could get the model to match. So just to summarize what was going on there, we had these MABR units up here, followed by conventional activated sludge. So if you go ahead and read that paper, it goes into quite a bit of detail about comparing that place, that sort of particular setup with and without the MABR units. I won't go into that part of the paper. What I really want to show you is the calibration of the model and how well we were able to get it to fit. So what we're seeing here is the feed these concentrations for soluble COD, ammonia, NOx, and soluble phosphorus. You can see the feed plus the RAS, and then those 4 reactors that I just showed, and then the effluent. So we wanted to be able to get the model to, of course, match to the data that's here. The data is the blue line with the dots, and the model is these pink bars. So it took a while to calibrate this, of course, and we needed to be able to make sure we had a good characterization of the influent. That was one of the key things. If you are in the process of trying to calibrate a system for denitrification, it's always important to make sure you have good characterization of your influent, to make sure you have the right amount of available carbon that might be relevant in your particular case, as it was here. And actually the ammonia fit actually very, very well. That part we didn't hardly have to touch at all. And once we got that soluble carbon calibrated and our influent characterization, our denite came in and snapped to right away. So aside from something that happened in that clarifier. There was a little bit of difference here that didn't quite match. Everything else matched really quite well. So we were very happy with the way that that turned out. And if you would like to dig into in a lot more details about how that model was fit to this particular set of data, that paper will be there for you to take a look at. I will go on and mention in a little bit more detail here one of the interesting aspects of things you can do with the model. One of the things that, of course, we're predicting is the distribution of the biomass in that biofilm. So in that example that I just showed you there for the hollow fiber, where I was showing about how the autotrophs grow on the membrane side, grow close up to the side to the membrane, and then the heterotrophs tend to be more evenly distributed or even a little bit preferential to the outside. Those are actually shown in these model results here as well in the pilot. So just to orient yourself here, this is the membrane side. This is the bulk liquid side over here on the left, membrane on the right. And we can see here that the DO, which is in blue, of course, is high, and then it kind of peters out and basically is zero by the time we get to the bulk liquid. And we can see that the ammonia is lowest up here against the membrane where all that oxygen is, and our nitrate and nitrite is the highest. But of course, those drop off as we are getting closer to that outside liquid there as well. So this was really quite illuminating to see it, be able to see how that fits and tell that same story here by looking and seeing the heterotrophs kind of more concentrating on the outside and the AOBs and the NOBs on the inside. Same story there. So that has proven out to work and fits within the way that we calibrated this model for this particular pilot. Okay, so just to conclude, we have those two MABR units in GPS-X, the hollow fiber and the flat sheet. And they can be configured and calibrated to those types of leading technologies that I mentioned earlier. I have seen all three of them successfully calibrated using our model. And as always, when you're doing that, it is important to keep in mind the influent characterization. So make sure, particularly, as I mentioned, if you're calibrating a DNITE system, make sure that you've allocated your inert COD materials appropriately. We've had lots of success using those, and I know quite a number of our clients have presented other papers based on results from our models as well. And so we've got lots of opportunities out there to take a look at other presentations too. So the interesting thing is to be able to dig into all of that voluminous amount of information that the model will output for you, the biomass distribution, the way that those nutrient profiles change as you go into the biofilm or as you look at the biofilm at several points along the plug flowness of those systems in series. They really do give you valuable feedback. And it's really interesting to do, bring in a recycle or look at changing the amount of air that you're providing, or any of those elements, and see how the shape of that surface changes as you maybe could optimize your system as you go.